Now let's prove E equals mc². First of all, the kinetic energy when an object with mass m moves at velocity versus can be expressed as follows. E equals 1/2 mv². Here we see that the mass m of the object and the kinetic energy E are proportional to each other. Next, let's think about the energy of light. The shorter the wavelength of light, the higher the frequency and energy. The energy E of light can be expressed as E equals hf, where h is the Planck constant, and f is the frequency of light. Now let's combine the two expressions. Considering that the mass of an object is proportional to the energy of light, the mass of an object with the energy E of light can be expressed as follows. M equals E, c², where c is the speed of light. As shown in this equation, the energy E and mass m of light are interchangeable, thereby proving E equals mc². Therefore, mass and energy are interchangeable and the speed of light is constant for all observers. It has a very important meaning that the mass of an object and the energy of light can be converted to each other. For example, the energy released during the splitting process of an atom is represented by a change in mass. These principles play an important role in achieving technological advances such as nuclear power and atomic bombs. In addition, E equals mc² has changed our understanding of the concepts of time and space as we perceive it, along with other results from the theory of relativity that the speed of light is constant. Relativity theory shows that time and space are relative, and can appear differently among different observers. Finally, E equals mc² is one of the most important principles in modern physics. The principle of E equals mc² is used in quantum field theory, a theory that integrates quantum mechanics and relativity, or cosmology that studies the structure and evolution of the universe. In addition, this principle plays an important role in the process of fusion and fission. E equals mc² is an expression derived from relativity. The theory of relativity is a theory proposed by Einstein, based on the constant speed of light and the relative motion of the observer that time and space feel different. In this theory, mass and energy are interchangeable, and E equals mc² represents it. Here, E represents energy, m represents the mass of an object, and c represents the speed of light. C is a constant value of approximately 299,792,458 meters per second. E equals mc² can be derived as follows. When an object is at rest, energy E is expressed as static energy, not kinetic energy. This static energy can be expressed by the following equation. E equals mc², 1. Here, m represents the mass of an object. Now, if an object moves, energy is converted into kinetic energy. In this case, the kinetic energy can be expressed as follows. E equals 1/2 mv², 2. Here, v represents the velocity of an object. However, in relativity, when an object moves fast, its mass increases and its length shrinks, resulting in different values of kinetic and static energy. Therefore, if an object moves fast, the kinetic energy of the object must be modified as follows. E equals gamma minus 1 mc², 3. Here is a gamma factor and is defined as follows. Gamma equals 1 sqrt 1 v² c². Therefore, the kinetic energy of an object can be expressed as follows. E equals gamma minus 1 mc² equals 1 sqrt 1 v² c². 1 mc². In summary, we obtain the E equals mc² expression, which shows the relationship between mass and energy of an object. E² equals mc² squared plus pc squared, where p represents the momentum, in general. Finally, the E equals mc² expression indicates that the mass and energy of an object are equivalent to each other. The formula plays an important role in a variety of scientific fields, including energy generated by collisions between electrons and positrons, and energy generated by fission. So what is the destructive force of a gram of matter when it is converted into energy? If a gram of material is converted into energy, the energy produced by the equation E equals mc² is calculated as follows. E equals 1 gram, 5. 299,792,458 meters per second, squared equals 8.99 times 10 to the 16 J. So, if we convert all of the material in 1 gram into energy, this energy is equivalent to 8.99 x 10 to the power of 16 J, which is about 90 trillion J. This is an unimaginably large amount of energy. How much of this destructive power depends on how you use this energy, but for example, in the case of an atomic bomb, this energy can be used to cause a lot of destruction. In fact, the atomic bombs dropped on Hiroshima and Nagasaki in 1945 were created using a gram of mass, resulting in enormous damage. So, this very large energy can be very destructive. How much destructive force does a gram have and how many kilometers of radius? Converting all 1 gram of material into energy produces energy of approximately 8.99 x 10 to the power of 16 J. At this point, the destructive force of energy is directly related to the explosive energy, which depends on various factors, but can be estimated roughly. Take an atomic bomb, for example, and explosive energy is measured in tons. There is no formula for converting explosive energy into tons because there is no fixed ratio between explosive energy and tons, but there is a formula commonly used for rough estimation. According to this, the explosive energy of a ton of TNT, total explosive, is about 4.184 times 10 to the 9 J. Therefore, the energy generated by converting all 1 gram of material into energy, 8.99 times 10 to the 16 J, is converted to the explosive energy of 1 ton TNT, which is as follows. 8.99 x 10 to the power of 16 J divided by 4.184 times 10 to the 9 J ton equals 2.15 times 10 to the 7 ton. In other words, if all 1 gram of material is converted into energy, it can be estimated to be equivalent to the explosive energy of about 21.5 million tons of TNT explosives. The destructive power of this energy is very large, and the destructive power over a few kilometers of radius can vary depending on various factors such as topography, atmospheric conditions, shape and size of explosives.